So what I wanted to speak a little bit about is how you sort of design for failure, right? In today's world, you have like a bunch of different microservices, and how do you sort of gracefully recover, or what do you do when different services start to fail? So this talk is sort of heavily influenced by two things. First is Release It. This is a great book by Michael Nygaard, and this is also based somewhat on a talk by an ex-colleague of mine, Smith, who spoke on called on at Garden City Rubicon. I've had the pleasure of working with both of these people, and they're both really great. If you can follow them on Twitter or whatever, yes, please do. Uh, right. So, like, I actually came across this tweet a few days before I gave this talk the first time. It said, "All programmers are time travelers. They travel to the future in their heads every day. The novices travel to the success of their programs, while the master travels to all possible failures as well." I think that's sort of a great, random tweet to pull out, to kind of get this talk started. So when you're dealing with different services, things will fail, right? There's a lot of reasons that things could fail. Your network screws up for whatever reason, like some sort of network interface goes down, or something breaks that way. The most common thing that I've seen in the SQL world is your database might lock up, right? So you have maybe a bunch of fast queries and one slow query. And what happens is that one slow query causes locks up the database. It like grabs a lock, or it just puts so much pressure on the database that your quick other queries get slow, right? So your database can definitely lock up. Maybe your caches are cold. For some reason, Redis evicted everything, and like everything is hitting the DB where it used to be only 10% of queries hit DB. So things will happen and things will fail. So let's take a very simple topology, and actually let's see what sort of happens over here, and how we can recover from this. So so over here I just have two services. I have A and B, right? So A has a database, and 95% of all requests that go to A are served by the database itself. About 5% of all requests go to the service B. Yeah, this is a pretty simple and very common use case. So what happens if service B fails, right? What happens when service B is down? How do you sort of recover from this? Right? So when I came out of college, if you had asked me what do you do when things actually fail, I'd probably tell you something like just retry it 5 times, right? So over here, I have a very simple example. I create a HTTP client with a max timeout of 5 seconds. And basically, I do a for loop, and where I less than 5 do the actual API call. And if this passes any once out of these 5 times, then it's a success, else it's a failure. So what could possibly go wrong with this? So it turns out that the various lessons from queuing theory are actually applicable over here, right? So your API is sort of, you can model it as an MMCK queue, right? Where the first M stands for the arrival rate. The second M is the rate at which you service these requests. Here, the word M stands for Markovian, which basically means that they sort of arrive in a bell curve with time, and they get processed in a bell curve. Where C is the number of servers, so that's roughly equal to the number of server threads that you're running slash the number of cores. It's in the tune of that. And K is the maximum queue size, right? So let's assume that your TCP queues can just back up forever, right? Like maybe you have some number of threads, and everything, all other requests will wait. So let's actually plug in some numbers over here. Let's actually take a pretty low request rate. Let's just take 20 requests per second, right? So with our new failure and our retries, we do 5 retries and 5 seconds each for the connection timeout. So the average service rate becomes 5% of requests take 25, and 95%, let's just assume 0. Let's assume that the remaining requests take nothing, right? So that's 1.25 seconds. So that's the average service time. So what is the average wait time for an MMCQ for different C, right? So if you have 30 server threads, then your wait time has suddenly increased to 978 milliseconds. That means even the requests which took 0 time are now taking 978 milliseconds, and the requests which took 25 seconds now take 25.9 or well 26 seconds, right? And if you actually have less than 25 threads, your system actually just never becomes stable at all. Your input queue will simply queue up until eventually you run out of memory, or something else shuts it off. So this is actually something that's called a cascading failure. Because if you look at it, due to the service B failing, and only 5% of requests were ever meant to go to B, service A is now slow, right? All requests to service A is slow. And let's say you had another service that depended on A, suddenly that's going to see an elevated response time. And then any service that depends on that will also see an elevated response time. So in this way, this sort of failure that has happened in B has cascaded all the way to every single service, potentially taking down your entire network. And that's why this is called a cascading failure, right? So the lesson that we have over here, or the lesson that we want to apply, is that it's often better to fail fast rather than succeeding very, very slowly, right? And this might also have different implications for your domain as well, right? That maybe maybe you've retried, and maybe there's a chance that actually the request went through and it caused some side effect over there, and then trying the second time might have actually caused more sort of problems, right? You've built up a distributed transaction sort of that way, and you're gonna you've done half of it that way. So in many cases, it's actually just better to say that, okay, fine, I think this is gonna fail. So this request is gonna fail, so let me just fail quickly rather than spending a lot of time trying to figure out if it's gonna fail or not. Which brings me to the next question, right? So let's say you have a bunch of you either do retries, or maybe you don't do retries, maybe you just do one call. What happens when service B finally wakes up? What happens when service B finally becomes healthy? So it turns out services are a little bit like people, right? So if you wake up first thing in the morning and before you brush your teeth, or I don't know if you have coffee or whatever, you'll be a little bit groggy and you're not really at sort of peak performance. Services are sort of a little bit the same, right? As soon as your service starts up, it's very likely, if you had some in-memory caches, those are not warm yet. If you had like sort of a just-in-time compile optimizer, like say the JVM hotspots, those haven't sort of kicked in, haven't kicked in yet. So branch prediction, those sort of things are not there. So generally, services will not be sort of performing at their peak performance. But suddenly, the minute it shows up, there's a large number of requests that have been queued up that this has to respond to immediately. And what happens is, as soon as service B wakes up, it starts getting so many requests that it immediately gets overwhelmed and shuts back down once again, right? So this concept is called as back pressure, right? So back pressure is basically these requests that have been queued up while your service was down, right? And again, the same things sort of apply, that you want to avoid this sort of back pressure as much as possible. Because let's even be honest, if your request has been already delayed by like 5 seconds or 10 seconds or whatever, there's even a good chance it may not even be valid anymore. Let's say this was like a thing which your actual customer and user was seeing. There's a very good chance they would have already closed the site and moved on, right? So old requests are generally not as valuable as the new ones, and plus you don't want these old requests to be bringing down your service again, right? So the lessons from these two together sort of come into what's called the circuit breaker pattern. Okay, so in essence, a circuit breaker sits before you make a cross service call. Yeah, so this sort of wraps all your API calls between one service to the other. So circuit breaker is either in the closed state. So in the closed state, it'll send all requests, right? So if A is making a request to B, when the circuit breaker between A and B is closed, all requests go through. But if the error rate, right? So if like a certain number of requests have an error, maybe like say 30%, or maybe the average response time for this, this entire operation goes above, say, 1 second, then your circuit immediately opens, right? And when your circuit is open, what the circuit breaker does is it just simply does not send any requests over to the next service. It will just immediately fail, basically sort of as no op. You'll basically get an exception or an error immediately saying this circuit is open. And to sort of complete the pattern, what you can also do is you can sort of give it an alternate function, right? So you can kind of say, for example, what we sort of do in slash GraphQL is we're trying to make an API call to some sort of external service. And if that service is down or is the error rate is too high, don't even bother hitting that service. Just try to read whatever data we have cached or have locally available in Badger. So that's talking about how the circuit breaker closes. How does the circuit breaker open again? Well, so when I said the circuit breaker sends no requests through, that's not entirely true. What it'll do is send a minimal number of requests through. So when the circuit breaker is open, like it might send maybe one request every second or so, so on and so forth. And with that request, it'll just basically poll, is the service B up and ready again? Yes, maybe the service is up. Let's start sending 10% of traffic, 20% of traffic. Okay, fine. It looks like service B is back up and ready. Time to close again and send the full amount of traffic back. So the circuit breaker basically protects service B by running in service A and stopping all traffic before it even goes outwards to service B. And so for a long time, the golden standard for this is a library called Hystrix. Hystrix is unfortunately Java only, but this comes from the team at Netflix. So let's look at this. Let's look at this command. So I just have a very simple thing. I have a class called place order, which extends my Hystrix command. It's initialized with some order details, and it basically says that this is part of the order service command group. So if order service is marked as down, all the commands will all the commands that depend on that will suddenly open up and stop sending requests. So you can see the second function, that's the run function. You can sort of think of this as plan A, right? So when the circuit when the circuit is closed, then it will call order service.place order, right? But if this throws exceptions too many times, or it's taking too much time, or whatever, the circuit is closed, or even if this run causes an exception, it'll then call the fallback, right? And so the fallback basically says, failed orders logged to the right to order detail. So in essence, what I'm doing over here is I'm saying I can't place the order. What I'm just going to do is I'm going to write this to a log file, and maybe I'll deal with this later. Maybe once a day I'll have a cron job that wakes up and says these were all the orders that were failed. Let's see what I can actually do. And I just have the usage at the bottom where you say new place order or execute. But there's many. But that's the syntax. It's as simple as that. And Hystrix will automatically do this calculation, and there's many configurations to say what's the rate when it's open to send through, what's the rate when it's closed, so on and so forth. Let's take this is sort of an example of a write where the write is failing. Let's take an example of like a read, like what's the common pattern. And this we're actually doing somewhat in Slash. So I have a read. I want to read an order from a service. So you can see my run sort of does a service.fetch by ID. And if it works, then I write it into a hard disk cache. For example, I could write it into Badger. And in the fallback, what I'll do is that I'll say I'll try to read it from this, from the hard disk. But in case that doesn't fail, yeah, okay, there's still a failure, so I'm just going to throw an exception. But at least some of the requests will, will even pass with some amount of sort of stale data. Okay. So Hystrix also provides like a great monitoring dashboard, and it sort of looks somewhat like this. So you kind of have like you can see over here there's like four different circuit breakers. It tells you what's the rate of each one, what's the mean, median, like response time, and there's this sort of gives you in some sense your app health, like for that single machine or that single service. It sort of gives you that health, sort of at a snapshot. Even if you don't sort of go with circuit breakers, another pattern that's very, very useful is called the bulkhead. Right, so this actually comes from ships. If you look at the bottom of a ship, the hull, in case that starts flooding, the entire ship will sort of go down. So what they do is even within the hull, there are different like sort of dividers, so that if this portion of the hull gets flooded, it protects the rest of the hull from flooding. Right. So in a way, so this sort of protects the ship from sinking as a whole, but it sort of compromises this part of the hull. And actually, that's a very similar pattern that sort of extends to building software, where let's say that like your service A that calls B, let's say that A dedicates maybe a group of 5 threads which are going to call B. So if these 5 threads are busy, maybe A won't even bother, right? Yeah, we're basically saying only these 5 threads can call B, and maybe there's like a queue in front of that, so you can put in things into the queue, and one of these 5 will process it. But as a result, not every thread will sort of wait on or like sort of attempt to do this. So this actually limits the concurrent calls, which could be kind of great for B if B is like a sort of sensitive service. And you're also in a position where if these 5 threads get messed up somehow, like like maybe all these 5 threads are just busy dealing with failures, the other threads are still fine. You're not sort of impacting those, right? Like obviously they'll just see that, okay, fine, this queue is full. I'll just sort of maybe skip posting to this or whatever. Hystrix does implement the bulkhead as well. You just have to pass a flag saying run on these sort of things. But this is something that I've seen implemented, even in Golang as well. So even though Hystrix is, by the way, Java only, I would say every language actually has a port, including Golang. But at some point, people thought that, okay, fine, like we've been doing services for quite a while. How can we make our life more difficult with Kubernetes? No, I'm joking. But in essence, containers are cheap, right? And in 2020, the majority of your APIs are HTTP based, where gRPC is also HTTP based, is based on HTTP2. So what sort of things can we do, like to kind of make this a little bit more scalable, a little bit easier to implement, and not as language dependent, considering that that everything is HTTP based. So let's look at this architecture again. I've just drawn boxes around it so it's clear who owns what. So I have service A that hits database, and then service B. And sort of the next evolution of this sort of pattern is to just put a proxy everywhere that you can find. So service A, all its input comes through a proxy. This proxy is called an ingress proxy. And the data, and when it's making API call outwards, it goes through a proxy that's the proxy sitting on P2. And then before the data comes into B, it comes into the ingress proxy of B. So basically every single pod or every single maybe like main container sort of has an ingress proxy for data inwards and egress proxy for data outwards. And this these proxy can implement different things like circuit breaker pattern or rate limiting pattern. But the beauty of this sort of thing is that these proxies can start becoming intelligent, right? So you can actually have these proxies can actually speak to each other and sort of become an intelligent service mesh, right? So let's take an example, right? Maybe service A, there's one container, and service B, there's 3 containers or 3 pods in the queue. I mean, they're not the same, but yeah, let's say 3 different instances of service B, right? So the ingress controller of service B, so that's 3 of them. So the 3 proxies, they know that the first one's response is maybe 10 milliseconds average response time. The next one is 15 milliseconds. The next one is 20 milliseconds. And it also, and this information is obvious, this information can obviously be calculated by the ingress proxy of each individual one. So these actually have the opportunity to kind of chat amongst each other, and then sort of inform the egress proxy of service A that, hey, maybe you should send less requests to this one because it's having a slower response time, and more requests to this one. Also between proxy, the egress proxy of one and the ingress proxy of the other, you can also do things like sort of check what the latency is between the two, right? Because you know that as from the output of service A, these are what these are the response times, and you can also check what's like the ping time between them. So you can also check that which of my which containers are sort of closer and which ones are a little bit further. and so on and so forth. And based on that, you can do like various sort of optimization. So generally, sort of like more intelligent routing, more intelligent load balancing, and stuff like that. So the current most popular one is something called Istio. And this is the visualization that at least the only visualization I can find. But Istio is built on a proxy that's called Envoy, and it basically will do these sort of things for you. Like if you have one service that's calling another service, it'll sort of measure what's the output rate for different instances of that service. I mean the response time for various instances, and how should I sort of route my traffic intelligently. And they kind of all talk to each other to be um, a bit smarter. And with that, I think that's the end of my talk. I just wanted to sort of, I guess my key takeaway or my key thing that I wanted to call out is that I guess the circuit breaker pattern is incredibly useful. At least when I first heard about it, I found it very counterintuitive that, if things are failing, you should just fail. I always thought, we should try to get a success at any cost. It didn't occur to me that, even that attempting to get a success will have somewhat of a negative impact. So that's sort of my key takeaway. And yeah, I'm now happy to take any questions.
One question I have, Tejas, is this something that we're using in Slash? And if we use it, then do we
Um,
use like any of these proxies, or do we use a library?
yeah, so we're not using a service mesh, even though like people have been trying to push this for a while. We are though implementing a circuit breaker. So very specifically, like when you sign up for Slash, you get an API key. And so, but we need to validate this API key more or less in every request to say, okay, are you a valid user for this database, for this backend, or are you not a valid user? Now, the current that would fail. So if API server is down, that would actually start failing. So, so what we're doing is a two-part thing. First of all, the valid API keys are sort of or valid and invalid API keys are sort of cached in memory for like 5 minutes, so that not every request goes. But there's a circuit breaker that says fetch from the API server and store it into Badger. And in case API server starts failing, at least whatever API keys are currently in your Badger will still allow those requests to come through. And we're basically depending on the heuristic that let's say API server goes down. Yes, new API keys they won't work, or API keys are not seen for like I don't know a week or a month. Definitely won't work. But at least people who are using their database in heavy load, it'll continue to work.
Hmm.
Tejas, I have a question. So you mentioned how you can use a proxy server to kind of emulate your uh, rate limiting and stuff like that, so that you know that you're not overwhelming a service that is already down. So my
Mhm.
question is, how would you design for a proxy getting overwhelmed? Like the proxy itself is a service that is based on the network and can get overwhelmed, right?
Good question. Yeah, that's actually a really good question. But it's not emulating the rate limiting; it is actually rate limiting. Basically, it will start giving 429s when you hit a certain point. So that is it's actually
Yeah.
down. So actually, that's one of the reasons that the proxies are deployed everywhere, right? So the reason that there's container ingress proxy, egress proxy is because the three of these are actually all deployed on the same machine. So because of that, they all work over the loopback device. The loopback device, so there's no latency between them. So it eliminates network failures. But obviously, there's always a chance that your proxy software itself can go down. But these are proxies that are specifically designed for these purposes. So they're sort of very, very, very battle tested.
All right. All right. Makes sense.
And they have to do lesser things, right? Also, like they do very less things. The service B is doing a lot of things, so it it might not get overwhelmed.
Yeah, exactly. They're very small surface area. They're only
But
meant to be load balancing and service management stuff like that. They're not yeah.
the service mesh that you mentioned earlier, do how do the proxies like communicate? So there are multiple proxies here. They would be having a common state somewhere, right? Do you have?
Yeah, I mean, if I'm being really honest, I don't know the exact details of how Istio works internally. Um, keep in mind that it's not exactly a common state. It's more of the state of the world as I see it, right? So in this example, I think V1, V2 are egress proxies. All V1 really cares about is that what is my individual latency to other things, or what do other people tell me their response times are, right? It's not really a shared state. It's really each
Okay.
each one sort of gets its own state, but maybe it can broadcast to other machines for informing, but it's not really a shared state.
Okay. Does any company use it, or some known service that we know of, like
Istio,
uses some?
Istio is actually Istio is very very popular actually right now. I don't know who it's from. I mean, I'm sure it's from some large company. I don't know who wrote it, but it's very very popular at this point.
Okay.
Let me check. If I'm not mistaken, I think Envoy was written from. Whatever. Yeah, I'm not sure. I'm not sure who wrote these. They're all part of the CNCF though now, the Cloud Native Computing Foundation.
All right.
Cool. I hope this talk was useful. I mean, the main reason I had given this in the slash team is to kick off the circuit breaker and stuff over there. But yeah, I thought this talk would be useful for the wider audience as well.
Yeah.
Cool. I guess I
Thanks a
ran over
lot,
time by
Tejas.
5 minutes. Yeah.
Thanks,
Thank you so much
Tejas.
for
Thanks, Tejas.
taking the time. Bye everyone.